Hello everyone and welcome to the first of several Physics 2 online lab simulation walkthroughs. My name is Alec Lancaster. I'll be one of your TAs this summer. And given the online nature of our class this summer, we thought it would be best to move our labs to these online simulations brought to us by the University of Colorado. But they can be a little tricky to run or use sometimes, so I thought it would be best to make videos of myself basically going through these simulations so that you at home can follow along with them. And really use these videos how you see fit. If you can't access or run the simulations, feel free to use the data that I take in these videos as your own. Or really, if you just want a guided walkthrough on how to do these labs, you can use these videos for that. So let's jump in. Today we're going to be performing the Incline Lab that should be assigned to you on the second or third day of class. I don't remember which. In any case, as I will say probably at the beginning of all of these videos, please read through the section in the attached lab manual. So this is, of course, just the online portion. Go ahead and read through the theory section of the attached lab manual so that you can understand kind of what we're going through and what kind of equations you'll be using and whatnot throughout the process of this lab. Next, go to this link here and go ahead and download the simulation that is found therein. If you can't run it for some reason, whether your Java's broken or whatever, you can just use this video as well. But I do think it is handy to be able to use these simulations and play around with them. But anyway, let's go ahead and get started. So first of all, you're going to want to have a timer handy. You can use a stopwatch on your phone or go to Google Stopwatch or whatever to use theirs if you'd like. But you're going to need one of those. Next up, open the simulation and run it, of course, and navigate to the tab on the top of the screen that's titled Friction, so not the first one, but the second one. Now, you have some options here. I've already done most of them, but go ahead and set the coefficient of static friction to 0.5, set the coefficient of kinetic friction to 0, set the box's mass to 100 kilograms, and make sure that the acceleration due to gravity that we're using is 9.8 meters per second squared, which, of course, is the Earth's value. And now set the object's position to 0 meters, which I've just done. One thing is that you can actually type in values in these boxes as opposed to using the sliders. I find that to be a bit more convenient than just trying to play around with the sliders and get those to work because it's a little tough. Next up, just make sure that the free body diagram is hidden because otherwise the screen just gets a little bit cluttered. Make sure that the friction setting is set to wood. Set the height of the incline to 0. You can do that by dragging this here or just, entering a ramp angle that corresponds with the height you're looking for, which of course in this case would be 0 degrees. Next, it says to turn the sound off. This isn't mandatory, but if you don't, it's going to make some really annoying crashing noises whenever it hits the walls, and it just gets really annoying. Right. Okay, so let's move on to taking the data. Now, I'm not going to write down the data as we go, so that will be up to you. I think these videos are going to help hopefully make things a bit easier on you guys, but I don't want to make it too easy by literally writing down the data for you. So, there's a little bit of legwork that needs to be done here. All right. What I think I forgot to mention was that we want to start the box actually at -5 meters. This is going to give us a decent time range to take our measurements over. And first, we're going to click the clear button to make sure that we're not recording anything currently. And what you're going to do is record the time that it takes for the box to come from just starting to move to hitting the wall here. So what we're going to do is use our mouse to apply force this way and give the box a little bit of a kick and then wait until it hits this wall here. So I'll show you what I mean by that. Alright, great. So the box is now moving and it's going to take a few seconds for it to move all the way to this wall. And once it moves to this wall, I'm going to hit this giant pause button here. Boom. Awesome. Okay, so the box is at 8.9 meters, which is good. That's exactly where the wall is. And now we're going to hit playback. And then what I can do here is I can scrub through this video, or just watch it, and figure out exactly at what moment the forces on the box, the horizontal forces on the box were gone, meaning that it's in motion. Alright, so now if I put the video normally to where it was, you can see the box is now just moving to the right, which is good. And what we're going to do is we're going to record the position of the box when it just starts moving. So go ahead and record that position as -4.6 meters. Or sorry, when there are no horizontal forces on it. So you're going to record that position as -4.6 meters. And now what I'm going to do, and there's a couple different ways to record the timing on this video. I'm going to do it in a way that's a bit more inaccurate than what you all are going to be doing probably. If you want to use this video to take data, I'll explain how to do that in a moment. But for now, I'm just going to record. I'm actually going to slow down the video, or for now, let's just record how much time it took to go from here to the wall. I'm going to record this on my phone. So, start, All right, so that took about 6 seconds. Okay, now what the lab manual tells you to do is to take that and to split it up into 5 equal chunks. Now the issue with that is that 5 equal chunks of 6 seconds is about 1.2 seconds, and the human reaction time to start and stop a video or a timer or whatever is about 0.2 seconds. That's a huge margin of error. So what you can do if you're watching this video on YouTube is actually just take the time difference between when the box started moving and hit the wall, and then pause the video at equal intervals. That way you're not introducing any timing constraints into it. And then when you've paused it and looked at the box at each of 5 different equal time intervals, you can just read the object position off here. So for instance, let's say, you know, at 0 seconds it's at negative 4.6, and like let's say after about a second it moves to here, then that's negative 2.8 meters, and then you move another second, and then another second, and then another second or so. You can just take those measurements by pausing the video, reading the timestamp, and then reading off the object position of the video, and then fill your table out like that. Again, with 5 points of data that are about equally spaced. Now I'm going to do something a bit different, and both are equally valid, but doing it using the timestamps on YouTube is going to be a little less inaccurate. So if you're going to do that, go ahead and skip through this portion of the video, or if you want to watch it to enlighten yourself, feel free. What I'm going to do is rescale the video so that it's going very slowly, and I'm going to record the time that it takes to move from negative 4.6 meters to 8.9 meters. So here we go. It's going to take quite a bit of time, probably about 20 seconds, I'm going to guess. But again, you don't actually have to do it this way. If you were doing it on your own and you wanted to use the simulation, you would have to do it this way, but otherwise you don't have to. Just, you know, use the timestamp method that I told you about on YouTube. If you have any questions about that, let me know. And hit stop. Okay, so that's about 18 seconds. Actually 18.25 seconds. So 18.25, and we want to split that up into 5 different time intervals. So we're going to allow the video to progress 3.65 seconds every single time. Again, my reaction time is probably about 0.2 seconds, so it's not going to be that accurate. But so call this time 0 and set the position to negative 4.6 meters. I'm going to start recording and move forward 3.6 seconds. Okay, so actually, at 3.75 seconds, the object position was at negative 1.8 meters. It doesn't have to be exact because, of course, this, due to the kinematics, whatever timestamp you take it at is going to follow the laws of physics, but we're trying to split it up as equally as we can. So I'm going to move another 3.6 seconds into the future, and then we'll record the position of the box when we get there. Okay, so at 7.21 seconds, the box is at 0.8 meters. And I'm just going to kind of fly through the rest of these. So we'll move forward another 3.6 seconds. Okay, so at 10.9 seconds, the box is at 3.5 meters. We'll go again. Okay, and at 14.38 seconds, the box is at 16 meters. And then we'll just let the video play out the rest of it. So at the end of the video, at about 18 or so, 18.25 seconds, we're at 8.9 meters. So you can use those as your 5 timestamps if you would like to. Otherwise, like I said, just pause the video at equal time intervals with the original time scaling and take the position of the box at that point. Okay, so moving on, we're going to go to the incline portion of this lab, and this is very similar to the setup of the last one, except with a few things that are slightly different. First, we're going to set the coefficient of static friction to 0.2. We're leaving kinetic friction and basically everything else as it was before, except for the incline of this wall, which we're going to set to 2 meters. And you can do that just by dragging the wall up and down. And then once you've done all of that, we're going to clear the recording so that we can record this next step. And what you're going to do is, it's actually a little tough. You're going to give this box a really, really good push such that it gets about halfway up this ramp. Doesn't have to be exact, but about halfway up this ramp and then falls back down back to its original starting point. So let's do that. Okay, that was a little too heavy, or a little too hard of a push. Let me try that one more time here. It might take you a couple times to get it right. It's a little bit of trial and error, so hopefully I can get it this time. All right, that was about halfway up, so we can take that. That was a fine take. We can use that. And then you're going to go to the playback section, and as you can see, the reason we're starting at -2 is so that it gets to 0 meters when there's no horizontal forces on it. So or at least, there's no horizontal forces on it at some point before 0 meters. So I'm going to set the normal timing of the video, and I will time it in the 2 ways like I did before, except that this time, because the timing is going to be a little shorter, it's going to be harder to do it the second way. So again, I would recommend, pausing this next portion of the video at equal time intervals, about 4 or 5, and recording the X position of the box at those times. So we're gonna go ahead and start it, and I'm gonna record it. Okay, great. So that was about 4.15 seconds. So again, just chunk that up into about 4 to 5 different pieces, and just scrub to that exactly on the YouTube video, and take the positions of the box that way. So like, this might be your 0 point, and then you might move 1 step here, 1 step here, 1 step here, 1 step here, right? And then just keep going forward. So to do it the other way, I'm going to slow down the video, and we're going to record the time it takes to do that. All right. So that was actually pretty much exactly 12 seconds. So what I'm going to do is actually just split this up into 4 different equal parts of 3 seconds each. That way, things are a little simplified. Okay, so we started here at about negative 0.8 meters. I'm going to chunk this up into different pieces of 3 seconds each. Okay, so at 3.09 seconds, the box is at 3.1 meters. At 6.14 seconds, the box is at 4.3 meters. At 9.24 seconds, the box is at 2.9 meters. And to finish off the video, at 12 seconds, it's at negative 0.8 meters, which is the starting point. Okay, once you've done all that, what you're going to do is some data analysis using the data you've taken and put into your Excel spreadsheets already. What's nice about Excel is that it lets you make graphs right out of the box. And so what you're going to do is, for the flat plane portion, determine the velocity of the object just after it's pushed and the velocity of the object just before it hits the wall. You can do that by calculating the average velocities in the first and the last time intervals of the video that you took, or the data that you took. And then using that, you want to calculate using that, you want to calculate the average velocity, and then you want to calculate the average acceleration of the box throughout its journey. The acceleration should be fairly easy. Velocity will be a little trickier because you'll have to do some actual math for that. But if you have any questions, feel free to let me know, and I can field those when the time comes. And then you're going to create graphs of the object's x position versus time, the object's velocity versus time, and the object's acceleration versus time. For the next section, what you're going to do, so this is the one with the incline. What you're going to do is make a graph of the object's x position versus time, just using the data that you already took. It should look roughly like a parabola. If it's not 100% close, that's all right, but really we're looking for something that looks like a parabola there. Next would be to determine the velocity of the object, the average velocity of the object in each of the 5 time intervals that you took. And you can use the formulas in the lab manual to do that. Then you're going to create a graph of the velocity versus time using the above. And once you've done that, your velocity versus time graph should look like a straight line, but not a flat straight line. So keep that in mind. And next, you're going to find a section within the velocity versus time graph that you just created, where the velocity is a relatively straight inclined line. It might not be like that the entire time, but find a time interval where it does look like that. And then for that stretch of time, you want to determine the average acceleration of the object within that time frame. Again, using the formulas that were presented to you in the lab manual. If you have any questions with that or the math behind it, do let me know. I'd be happy to answer those during help room hours or anything like that. And then lastly, you'll want to create a graph of the acceleration versus time, and that should look roughly like just like a flat straight line. So anyway, there you have it. Hopefully this video is able to enable you to take the data for yourself, or you could use the data that I took here. If you have any questions, feel free to let me know, and I would be happy to cover some of those.